Hello, folks. Dr. Cole here. Let's move on to our lecture on using JASP to conduct logistic regression. Okay, make this a little bit larger. Okay, so let's do a review. Regression analysis is a statistical tool used to explain the relationship between a response variable, which we also call the dependent or the outcome variable, as a function of one or more predictor variables that we also call independent variables, or sometimes factors. In linear regression, we assume this relationship can be explained with a linear function. When the dependent variable is continuous, the ordinary least squares method is used to explain the linear model. What if the dependent variable is not continuous? Well, if the dependent variable is a categorical variable, it's best practice to use alternative regression models. And one of those that we're going to learn today is logistic regression. So let's first review what categorical variables are. A categorical variable only takes one of a limited number of possible values, often representing groups based on underlying quantitative variables. If there is no natural order or rank between the groups, the variable is called a nominal categorical variable. In the case where we have a categorical variable that is binary, so a binary nominal dependent variable, for example, the outcomes or the responses are yes, no, or success, failure, or hit, miss, or disease, no disease, male, female, etc. Binary logistic regression is a really good model to use. The model includes one or more continuous or categorical independent variables, so just like we did with linear regression. Only in this case, our regression coefficient is built on not the ordinary least squares method, but it's based on modeling a logistic function, which transforms a linear combination of coefficients and predictors into probabilities. So whereas when we did linear regression, we had in the units of our variables a 1 unit change in the independent variable. When we look at the unstandardized regression coefficient, that's going to tell us how much of a change in y is occurring based on the units of the independent variable. And then, of course, you know that we could get the standardized regression coefficient, which standardizes it as a z-score. So we see everything as a function of standard deviation units, that y will change. The dependent variable will change as a function of a unit change in the independent variable. Well, in logistic regression, our regression coefficient is basically going to be probability, or in this case, the odds that the dependent variable changes as a function of a unit change in the independent variable. So really, how does logistic regression work? Logistic regression is predicting the probability of our outcome variable based on the independent variables. For example, let's suppose that the dependent variable is the presence or absence of a disease. So logistic regression calculates the probability of the disease being present as a function of the independent variables, and the probabilities, because probability goes from 0% to 100%. So when we turn that into numbers, it's 0 to 1. All right, so the key difference is that unlike linear regression, where the outcome is directly measured, logistic regression is modeling the probability of an outcome. In other words, in linear regression, we have all of the scores of the dependent variable in our data set. And what we're doing is we are generating the best fit line that models or regresses the y, the dependent variable, on the independent variable, or the set of independent variables. And logistic regression, what's happening is you're measuring how many times, for example, the disease occurred in the data set, how many times the disease did not occur, because that's an outcome variable. And then the statistics are modeling probabilities of trying to get as close as possible to what the data actually are. All right, so we'll see what's going on here. So let's use a data set called ELS 2002, which is data from 15,370 students on their academic performance. And in particular, I just pulled out, this is a big national data set that you can access. I'm not going to go through the process, but you can look it up and you can see that you can grab that data. It's pretty cool. So I've already downloaded it. I've already cleaned it. I've already put it in JASP. So we're going to work directly from a JASP file. So what you want to do is click on this link and you'll see this button. And then you click on this button and then you get this thing. But what we want to do is download the file. And once it's downloaded, it'll go into your download folders or wherever you've asked your downloads to go. And now we've got a JASP file that's ready to double click and open up directly in JASP. So let's take a look at the data. So you see we have, get this out of the way. We've got sex, race, grad school, prep, writing, SES, and SESQ. So let's edit the data and see what we really have. Right, so I just double clicked on sex. So you see we have male and female. Race, we have Asian, Black, Hispanic, white. The reason why I coded these both as Hispanic, because 4 in the original data set was, I think, well, there were 2 different ways that people could identify themselves as being Hispanic. Grad school, I've got 1 is yes and no is 0. And the way logistic regression works is the first class, whether it be number 1. So in this case, the first class is 0, or what they call the first level. That becomes the reference class. So the probabilities that we'll be looking at are yes versus no. If we reordered it when we did the analysis, now it would be predicting no versus yes. So that's how logistic regression works. Much like we learned, I think we might have demonstrated before when we were doing categorical variables as independent variables in the linear regression. It's whatever is your 0 class is what the coefficient is being compared against. Okay, it'll make sense in a moment. Prep refers to class preparation scale. So it's a continuous variable, but it's been standardized. So it has a mean of 0 and a standard deviation of 1. So any changes are about how many standard deviations above or below the mean. We're not really concerned with the actual scores of prep because we've standardized them. And that by doing that, we can compare a lot of variables that have been standardized, which is what's convenient about standardizing variables. And then writing is a writing ability scale, and SES is socioeconomic status. Socioeconomic status is a measure of access to resources. So low socioeconomic status means low access to resources, education, and opportunities. High access means high access. And then I've already created the categorical SES in 4 quartiles using the formula because I took SES and I said, give me quartiles. Quartiles is 4 equal groups, right? Quartiles or cut points for 4 groups is the same thing. So you can see -5, 0.04, 0.59. So -5, 0.04, 0.59. And then if it's none of those 3, then it's going to be group 4. So we've already done that. Okay. The data are finished. And now we can start to experiment and do our analysis. Okay. So let's explore, or let's investigate the probability of attending grad school. So grad school is going to be our dependent variable for all of this, including your assignment. It's the probability of attending grad school predicted by sex. All right, so let's go ahead and do it first in JASP, and then we'll explain the results. Okay. Analyses, regression, logistic regression. Okay. Now let's put in grad school as our dependent variable. And you can see already before we do any predictors, the data alone are saying that there is a significant prediction of being in grad school just among all the data. And we'll clarify that in just a moment. But you can see what it's doing is it's saying what we're seeing is the results for yes. So we're predicting yes. Okay. Now, our predictor is going to be sex. So we'll put that down here as a factor. So it's added in sex. Okay. Now we have to go down here. So we'll get to this in a moment, but model is just like we learned before. We could do a hierarchical model. We can do interactions. We're not doing that just yet. The statistics, I want you to click on odds ratios, confidence intervals, and odds ratio scale. And then go down to the plots, and I want you to click on conditional estimates plots. Okay. And in the conditional estimates plots, there we're seeing the probability of attending grad school, whether you're a male or female. And we can tweak this just a little bit to make it easier to see these probabilities. So we can go to edit image, and let's adjust the y-axis just because we've got a lot of space that we're not seeing. We're going to specify the sequence. We're going to say, give us the steps. Instead of 0.25, we'll do 0.1. So we have a little more, it's a little easier to see where kind of we are. And then in advanced, we're going to set the lower limit to maybe, how about 0.6? Let's do 0.5. Right, so now we've just made it a little bit easier to see the results. We can see males given no other prediction. If you're a male, there's an approximately, what, a 71% probability of attending graduate school. And if you're a female, there's an 80% probability. So females have a higher probability. And that's what we see here then, because we're looking at the prediction of females, the prediction of attending grad school for females relative to males, right? So males have an odds of 2.5, and females are 1.4 times more likely to attend graduate school than males. Let's explain that again here. So what we have in this analysis is we're examining sex as a predictor of the likelihood of attending graduate school. We had graduate school measured where 1 is attended the graduate school and 0 is did not attend. And sex was measured where we had male was really 1 and female 2. So that's another way of saying male was 0 and female was 1, because it just, JASP doesn't care the actual numbers, it just cares the order in the day that we've set up the analysis. So we've said 1 is the reference class. Okay. So this is what we just did. And now let me help you understand it. So we're looking at model 1. We're not going to really be concerned with model 0 in these. But model 0 is a way to get you an idea of what's happening before you add in any predictor. So it's just like what's built into the data. Well, what was built into the data is that there was a higher set among a higher number. I mean, we can just double check right now. Descriptives, grad school by, we're just looking at grad school, and let's look at the frequency. So, right, so just built into the data, we have a higher frequency. We have 75% more of the students reporting that they attended grad school than not. And so this model 0 is telling us that right off the bat, we have a data set that's highly predictive of attending grad school. But we're really interested in the model 1, the model where we start adding in the predictors. So the odds ratio for the intercept is 2.506. This represents the baseline odds of attending graduate school for males. The odds ratio for sex is 1.483, meaning females are about 1.5 times more likely to attend graduate school compared to males. The confidence interval is 1.37 to 1.605. Now, if the odds were 1, that's like a correlation of 0. There's no relationship, right? There's an even probability of being in either group. So that's like saying no effect, no odds, right? So in this case, when we talk about odds, it's 1, right? A 1-to-1 relationship means there's 1 over 1. There's no different. There's no change, right? Because it's a ratio. And so if your confidence interval has the number 1 in it, then the p-value, which is in this case in logistic regression, it's a p-value that is being generated according to a walled statistic. And whereas in linear regression, the p-value is being generated from the t-distribution or the t-statistic, but we interpret p the same way. If p is less than 0.05, it's a significant effect. And so since the confidence interval does not include 1, it indicates statistical significance, but we also have the p-value. But it's always good practice to report an odds ratio plus its confidence interval. So the p-value, which in this case is considerably less than 0.001, but 99.9% level of significance, confirms that the effect of sex on graduate school attendance is statistically significant. All right, let's talk about the plot. This is what we call a conditional estimate plot. That's why it's called an estimates plot. It's visually plotting then the probabilities from the estimate. So what it's doing for us without us having to do the equation, although you could run this in ChatGPT if you want, it's taking this logistic regression coefficient, which is called an estimate, and it's really what is called a log odds value, or they call it a logit or log it. but it's what's called the log odds. So a log odds of 0.394 is equivalent to an odds ratio of 1.483. It's also equivalent to a probability of 71%. So we don't have to calculate it, but like I said, if you really wanted the exact numbers, I mean, you could go to ChatGPT and even I think the free one does this. So the free one is mini. I don't have it here because I'm in my logged in version. But if you go, what is the probability of a log odds equals 0.318? Is that the value? Zero 0.394. 0.394. So it'll give you the formula, and you can see it's using E. It's complicated. It can be done easily in Excel because Excel has a function for that. So let me see. Why did that do that wrong? Okay, I see I did wrong. So yeah, that was correct if we were just saying 0.394, but really the way that you need to do it is first you start with the males, which is 0.919, and then females would actually be 0.919 plus 0.394. So and actually they've done it here, right? So the log odds for males, 0.994 is 72.9%. I think I might have entered those numbers wrong. What was it? 0.919, 0.394. Log odds of 0.919. So the males would be 0.919 and the females are going to be 0.919 plus 0.394, which is 1.313. There's the formula. And then we can see that the males, the actual probability is around 71.5%, and females at 78.8%. You don't have to do that. I just wanted to show you how to do it. Bottom line is your figure is doing that for you when you have a categorical variable. We'll see what it looks like when we get a line. Now, when we have a continuous variable. Now, the other output that's important is just like in linear regression, we had the R squared that sort of told us the effect size and how much the proportion of variance or how much in the dependent variable that can be accounted for by the dependent variable. In logistic regression, it's the T-Zer R squared is usually the most common one that's reported. All these statistics over here are what we call model fit statistics that we're not getting into. So we have here a 0.007, so that's about 0.7%, not much prediction at all, right? So the T-Zer's R square is similar to R square in linear regression, representing how well the model predicts the outcome. Here, a T-Zer's R squared of 0.007 means the model explains only 0.7% of the variance in the probability of attending graduate school. This low value suggests that sex is a statistically significant predictor, but not a strong one, highlighting that additional variables are needed to better explain graduate school attendance. Okay, so in this example that we just did, the odds ratio was above 1. So we're saying something is more likely to happen. The outcome variable is more likely to happen. And in this case, the outcome variable, since it was binary, was whatever the one class is, because the modeling is assuming the reference class is called 0. So in this case, the reference class is no. So here you're 1.5 times more likely to predict yes if you're a female than if you're a male. But what if the odds ratio is below 1? So it's a little bit confusing, but let me give you an example. So let's say we're trying to predict wine type. So in this case, our outcome variable, binary dependent variable, it's wine type, red versus white. So red will be the reference class. Red is 0. And then our results are about predicting white wine relative to predicting red wine. So, and our independent variable will be alcohol concentration, right? So you can see here, we're coding 0. Red wine is our reference class. So the results are about the odds of being a white wine versus being a red wine. Okay. And let's say we get these results, okay? And what do we see here? We see here that it's negative, so there's a negative relationship, and that's why the odds ratio is less than 1. And since alcohol is a continuous variable, and now we have the what the estimate plot is it's giving us an estimated best fit line of these probabilities with 95% confidence interval. So before we even look to interpret the odds ratio, just looking here, we can see what? As alcohol concentration increases, as there's more alcohol in the liquid, the probability that the wine will be white is decreasing, right? It starts at a probability, if we have an alcohol concentration of 8, it starts at about a 26% probability that it's going to be a white wine, and then it goes down from there. But more importantly, or in addition, let's understand what the log odds negative 0.065, which corresponds to an odds ratio of 0.937 means. So the odds ratio below 1 means that higher alcohol concentrations are associated with reduced odds of the wine being white. Alternatively, if we flip it around, as alcohol concentration increases, the odds of the wine being red increase. So practical. So this 0.937 odds ratio means for every 1 unit increase in alcohol concentration, the odds of the wine being white decrease by 6.3%. We've simply calculated that because 1 is 100%, and 1 minus the 0.937 leaves us with 6.3%. So we're saying, in other words, wines with higher alcohol concentrations are less likely to be white. And as that alcohol concentration increases, there's a 6.3% likelihood for every unit increase in alcohol concentration that it will be white. And we see on the visual interpretation, the plot, I showed you that probability. So when we interpret odds ratios below 1, they are reflecting a negative relationship, and we'll see that because the estimate will be negative, but then that's translated to an odds. So why do we use odds ratio? We use the odds ratio so we can have conversations. People understand when you tell somebody you're 2 times more likely, right? 2 times more likely is something that the medical field likes to hear. It's something that physicians like to hear. It's something that data analytics is a very, it's a good way of being a data analyst if you can use terms that people understand in their everyday life. 2 times more likely is 2 times more likely, right? If you have $1 and I multiply times 2, now we have $2. It's 2, we've grown by 2, what we call a twofold. What if we grow 10 times more likely? Sometimes people say a tenfold chance. Well, if you have $1, 10 times is $10. So on the alternative, if we say we're dropping by 6.3%, now that's helping us to understand that in a language, a use of words that people can understand. So they negative odds ratio below 1 reflect a negative relationship between the predictor and likelihood of the outcome. For example, the odds ratio 0.937 means that as alcohol concentration increases, the odds of the wine being white decreases, or the odds of it being the alternative, the reference class, increases. This reinforces how to interpret protective effects or inverse relationships in the logistic regression. And let me just say, since we're running the statistics, if at any time you'd want to frame it from, if you're getting a negative coefficient, you can always go into your data and reorganize the reference class. Like, let's just say we were interested in understanding the odds of not attending graduate school. Okay. So since we just flipped it now, it's going to be the odds of not attending graduate school versus attending. And now we'll see. So now we're predicting, no, well, now we have negative, right? You're less likely to not attend graduate school if you're a female than you are a male. The flip of that is you're more likely to attend graduate school if you are a female than you are a male. All right, so let's go back and fix that. So you see what I did? I just changed the levels for the reference, and that's, you can, you manipulate that. And now we go back. Now we're more likely to attend graduate school if we are female than we are a male. And in fact, how much more likely? We're 1.5 times more likely to attend graduate school if we are female than we are male. And in particular, females have an estimate of around 80% probability of attending graduate school. Males have about a 75% probability. Okay, next. Let's predict graduate school by a continuous variable, preparation. All right, I'll just demonstrate and then we'll look at the results. All right, so now let's put prep. And what is prep? Well, prep means it's a scale score. So there's a bunch of items. They ask students to self-report how prepared do they think they were to attend. And it's been standardized to a mean of 0 and a standard deviation of 1. So what we're looking at here is we're looking at the odds of attending graduate school increase by about 1.4. You're 1.4 more times likely to attend graduate school for each standard deviation increase in the preparation score. And so what we see then on our plot is these are the standard deviation units. So the mean is 0. So the mean probability for attending graduate school is 75%. The fact that even at the lowest reported prep school, there's a greater than 50% chance of attending graduate school just means that in the data set, people got into grad school even if they thought they weren't prepared, right? But we do see this upward growth, this 1.4 times more likely to attend graduate school as your prep score increased by 1 standard deviation is shown by the upward slope of the probability estimate plot, right? The T-shirt square here of 0.02 means not much, right? About 2%. So there's still other things that we need to add in to understand more what predicts attending graduate school. And I spell all that out for you here, right? So let's understand a bit more. So we start with an intercept. The intercept is a log of 3.2. That's the baseline odds of attending prep school, of attending graduate school when prep is at 0, right? So what's going on here then when you have a independent variable that's been standardized is our intercept is when the independent variable is absent or 0. Well, in this case, 0 is actually the mean. So those people who self-reported an average preparation score, they start off the bat at 3.2 times likely to attend graduate school versus those that don't have the 0. But what we're really looking at is how much that increases or decreases by increasing standard deviation units. So we see the coefficient for prep is 0.314, meaning for every 1 standard deviation increase in preparation, the log odds of attending graduate school increase by 0.314. That 0.314 log odds is translated into an odds ratio of about 1.4, right? So the odds ratio, meaning that for every 1 standard deviation increase in preparation, the odds of attending graduate school increase by 36.9%. So 1.4 or 1.36, let's do 1.4. 1.4 is equivalent to 40%. So you start with 1, and then anything above 1 is the percentage increase. So if you had an odds ratio of 2, starting with 1, we have 100% increase. Saying 100% increase is meaningful, but so is saying 2 times. So in this case, saying 1.4 times has meaning. The practical meaning is 40% increase. The probability estimate plot shows preparation is a significant factor. Higher prep scores lead to higher probabilities of attending graduate school. We're seeing that here. At prep, when it's -3 on the axis, that's what I talked about, that is slightly above 50%, indicating according to the data in the model, even students with very low preparation still have a better than even chance of attending grad school. At prep equals 0, which is average preparation, the predicted probability of attending grad school is approximately 75%. And by the time we get up to 2 standard deviations, we're about 75%. And no, at prep equals 0, we're at 75%. By the time we get to 2, we're at 90%, right? So we see here when prep is 0, it's about 75%. Going up 2, it's about 90%. Let's not get confused between the likelihood and the odds ratio. The estimate plot is giving us the likelihood. So this is also great for data analytics. This is a great visualization. The odds ratio is telling us the odds of getting into grad school relative to not getting in grad school as a function of the unit increase in the continuous variable, or if the independent variable is categorical, the class that we're referring to, that relative to the reference class. When we did sex, it was female was the measured class versus the reference class, which was male. In this case, the odds increase by 1.4 times, or 40% increase. How does that translate to probability? That's the estimated plot. The probability of getting in grad school, if you have an average preparation score, is about 75%. The probability of getting into grad school, if you have self-reported preparation score that's 2 standard deviations above the mean is about 90%. All right. And then the teaser, what was the teaser here? It was 0.02, so it's about 2%. So what does that mean? On average, the model predicts a 2% higher probability of attending graduate school for those who actually attended compared to those who did not. And the teaser indicates that the model using PrEP as the sole predictor, because it was the only one we put in the model, it has limited what they call discriminative power or predictive power. While PrEP is a statistically significant predictor of graduate school attendance, it explains only a small part of the difference. All right. Let's take a look at something that's a little more complicated when we have a categorical variable that has multiple categories. So in this case, let's look at race. All right. First, let's take a look at race. So race, the first class in the order, whatever order we put it in, we can reorder them. But the first class is Asian, so that's going to be the reference class. That's like when we did sex, the first class was male, so that was the reference class. So we were looking at females relative to males. And in this case, we're going to be looking at whites, Hispanics, and blacks relative to Asians. So the intercept is referring to Asians. So let's do that model. So predicting grad school from race. All right. So, and again, to make it a little bit easier to interpret these, if you wanted to, you could adjust your image. We can leave this where it is now. And so what we're seeing is Asians is the intercept class, right? So Asians have a 6.5 times more likelihood of attending graduate school than the other race categories. Blacks, now they're all significant, right? And when we did the PrEP, that was also significant. And you can see, right, the confidence intervals, none of them include 1. They're either below or above, but they don't include 1. But look, blacks are less likely, right? It's negative. They're less likely to attend graduate school relative to Asians. And Hispanics are less likely to attend graduate school relative to Asians. And whites are less likely. How much less likely? Well, that's the odds, right? Blacks are 1 minus 0.328, so what, approximately 70% less likely than Asians. Hispanics are 75% or 73% less likely, and whites are about 42% or 41% less likely. And we see that here in the graph, right? The probability of attending graduate school if you're Asian is about 90%. The probability if you're black is about 74%. Hispanics have the least probability, but they still have a very good probability of attending graduate school, right? They're about 70%. And whites are about 80%. So we see all that represented here, and I explained it all here. Go ahead and read through this, right? Exactly what I said, right? Blacks are 67% less likely than Asians because of the odd ratio of 0.33. Hispanics are 73% less likely because of their odds ratio of 0.27, right? 1 minus 0.27 is 73. And whites are about 41%, right? 1 minus 0.49 is 41. In this case, we had the teaser of 2.6, right? 0.026 refers to a 2.6% discriminative effect. Still low, So race, while a significant predictor, is not much of a predictor overall of the possible predictors of going to grad school. How about if we do an interaction? How do we interpret an interaction? Well, let's look at prep as one variable. Let's add in sex. And just from those two, we can see they're both significant. We had learned that before. Prep was a significant predictor, and sex was a significant predictor. And we can see that here, same relationships. But now we want to know, is this effect of prep on predicting grad school somehow different for males than it is for females? So we need that. That's where that interaction term is that we practiced in the linear regression examples. So you know how to do that. We've got to go down to our model and we have to add in the interaction term. Unlike linear regression, where we could ask for change in R squared to see if there was a significant increase in model. In this case, we're not necessarily doing that. You could still do it because the models have model fit statistics, but we're not getting into that detail. But let's just practice anyways. I'll show you what's going on. So let's add another model, and now let's add in the interaction term. Okay, so whereas before we were using the F to F test to test if there was a change in R squared, now it's a change in the chi-square. But the point being, it's a significant. Adding in the interaction term is significant, and that's why we see down here that the interaction term is significant, which is why it's not really necessary to do it hierarchical. It's going to come down here in the p-value anyways. But if you want to do it hierarchical, that's fine too. Okay. So what do we see here? Well, the odds are slightly higher, 1.0 time, 1.09, 1.1 times more likely for females to be affected by prep in attending graduate school than males. It's a little complicated here. I wrote it out to help us understand what's going on here. Okay. So our odds ratio for prep alone was 1.3, right? For males, the reference category, a 1 unit increase in prep is associated with a 30% increase in the odds of attending grad school. Because we added in sex. So since in sex, males was the reference class, we need to understand what prep means. Prep is telling us the odds for males. Okay. Now, sex, since male was the reference class, now we're seeing the odds for females increases by 38%, 1.38 times, 30% higher odds. Now, what is the interaction? Well, the interaction is 1.09. So the interaction term indicates that for females, the effect of prep on the odds of attending graduate school is slightly stronger compared to males. Specifically, right? So 0.09 is like 9% higher than 100%. Specifically for each 1 unit increase in prep. So as the prep scale increases by 1 standardization unit, the odds of attending graduate school for females increase by an additional 9% beyond the base effect of prep for males. The practical explanation, the interaction suggests that prep impacts males and females differently in predicting the likelihood of attending graduate school. While prep improves The odds of attending graduate school for both males and females. The effect of prep is amplified for females. That's what the interaction term is telling us. Without the interaction term, we would have thought that prep on graduate school would be equally just, predictive among males and females, but we have a slight difference, right? It's significant, and it's slightly more of an effect for females than males. Okay. So that's your lecture. I've given you everything that you need to do. For your assignment, you're going to do grad school regressed on writing plus socioeconomic status quarterly, right? So here we have, and there's no interaction term. It's just, let's look at the writing score. So now we have the independent variable, which is a scale, just like prep. It's got a mean of 0 and standardization units of 1, and it's self-reported writing skill. I think it's actually test scores. How well did you write? And then we have socioeconomic status, which has been turned into a categorical variables at quartiles. And then for your second question, I want you to now do the continuous variable SES and the categorical variable race, but then do an SES times race interaction. It's going to be really interesting. Okay. So just like the last 2 lectures, do the analyses, share your screen, record yourself on Zoom, narrate the results, give an interpretation, give it your best shot. And thank you very much. Good luck. Bye-bye.